This video is sponsored by PCBWay. Welcome everyone. In this video I'm going to show you an interesting circuit. This has been shown in my earlier videos. I used it for some demonstrations. And in this video I want to move a step forward and further explain this circuit. So the circuit which is on the PCBs is inspired by this little circuit here. And you might find this circuit familiar because I used it in some of my previous videos. And also some viewers can find this familiar because they have been asking me about this circuit quite some time in the past few months. So then this video probably will be useful for them. So this is a very simple little strain gauge module. And it does nothing else than just picks up the bending of this little strain gauge here, and then by the built-in Wheatstone bridge and an operational amplifier, it just gives a signal which is proportional to the bending of this strain gauge. So what I did is that I took this circuit, I reverse engineered this circuit, and then I made my own, let's call it educational version. So these two guys are basically identical, but you can see that obviously this is small and it's more compact. But this, I plan to use this as some kind of educational board to help people to understand several different concepts. And those concepts are shown at the top right corner of this PCB. So with this circuit, we are able to study Wheatstone bridges and then operational amplifiers, more precisely differential amplifiers. And then, of course, we can study the strain gauges themselves, so these little guys here. So it will be very interesting to make this circuit work. And as you can see, all these circuits, they have the green PCB mask and white text color, so it gives a very nice contrast, as you can see. All the components are very nicely visible. And why I picked the through-hole components and why I picked this large, let's say, layout as compared to this very tiny layout, I think this board can be fitted on the green PCB like 6 times. But why I picked this is because I placed a lot of test points on this. So with this board you can not only just amplify the signal of a strain gauge and read it with something, but you can actually study the different let's say components of the circuit, and with that you can check your formulas, because each of these, let's say, sub parts, the Wheatstone bridge, the first stage of the amplifier and the second stage of the amplifier, can be like theoretically calculated, like what will be the output voltage here, what will be the output voltage after the first stage of the amplifier, and what will be the final output voltage after amplifying the signal for the second time. And yeah, that can be checked here with a multimeter, and obviously it can be calculated by knowing all the components. So what I will do is that before assembling one of these boards, I will pick all the parts which I already ordered and everything, and measure them. So especially the values of the resistors are very important because they determine the gain. So we will look at those, and then I will put together the circuit, do the measurements, and after that we will go through the circuit according to the theory. So I will check it, the measured values, I will check the measured values, and I will compare them with the theoretical values, and we will see if the circuit really does what the formulas predict. And since I reverse engineered this circuit, I will put the schematics and everything on my website for free, because yeah, I basically just copied someone else's design. So I think the least I can do is that this is just freely shared with everyone, so if you feel like, you can replicate this. But you can also go to the website of the sponsor of this video, PCBWay, and check my project page, because if you want to have this PCB to made, obviously that won't be free, but it will be very cheap if you order it from PCBWay. So head over to their website, to my project page, and select this board in your favorite color and in your favorite style, and then order it from them. And then once again, as you can see, everything is designed through the whole components, so it will be very easy to build it. And I will show you also in my video how it is built. So head over to PCBWay.com, check my projects, and order this PCB if you want to replicate this project. So as you could see, I assembled this circuit. So let me discuss the parts of the circuit, and then we will test it and see how this works, and then how it compares with this circuit right here, which is the, let's call it, reference for this circuit. So as I said, this is made of several modules. I will try to zoom in here. So this area here is a Wheatstone bridge, and you can see 3 resistors here, and the 4th resistor is on the right side here. That is the strain gauge. And then there is a trick with this circuit here. So if we check the components and the values on this SMD circuit, we will notice that each of these resistors are actually 348 ohms nominal resistance. I measured these, and they are more like 346.7-ish. But this guy has a larger nominal resistor. And when everything is put together here, the funny thing would be that this Wheatstone bridge, if this is the negative and this is the positive side, produces a negative voltage output. And that's the trick of the whole circuit, and I will tell you why that is a trick. So this Wheatstone bridge is there, producing a negative voltage. The Wheatstone bridge is, of course, powered by this Zener reference voltage source, which is a voltage reference of 2.5 volts. So that's why I have the VREF 2.5 here. So then we get the 2.5 here, and then here we get like a few millivolts, or even a fraction of a millivolt here. And then that goes towards these resistors, actually these 4 resistors, So they are the voltage dividers for the first stage positive input or non-inverting input of the op-amp. And then Fs minus, as it's also written down here, that's the negative or inverting input of the op-amp. And then the values of these two resistors, they are identical. So R8, R4 are identical, and R9 and R7 are identical. So we can just take the fraction of these two resistors, for example, R4 and R7, or R8 and R9, and they will determine the gain of the first stage, and that is roughly 50 times. So then the output voltage comes here at FSO, and then that goes towards another set of resistors and 1 kilo ohm potentiometer. And what this will do is a very funny thing. So here on the second stage, so whatever is marked by the double S here, so SS plus, SSO, and somewhere here there should be an SS minus. So these double S terminals are for the second stage. And then whatever we have here is making sure that we are not only doing another set of amplification or gain with the other op-amp in this package, but we can also shift the output voltage. And there comes the trick. So how this whole thing is wired up is that here we get a negative voltage, but then here we flip the polarity of the voltage. So at the FSO, so first stage output, we will get a positive output voltage, and then here that is further amplified while still keeping it positive voltage, so we are not inverting it. And then why that matters is that because here we have a single rail op-amp, which means that the voltage which could be covered by the outputs is in between ground or 0 volt and the positive input, so 5 volts roughly, if we oversimplify the things. So we cannot have, for example, negative voltage. And if you would use this thing, you would assume, let's say, that your baseline is at 0 volts, and if you apply tension, you will get, let's say, positive voltage output, and if you apply compression on this guy here, on the strain gauge, you would get a negative output voltage. But no, this is more tricky. So with this potentiometer, you can shift the output voltage between 0 and 5 volts. And what you could do, or what you can do and should do, is that with the unstrained strain gauge, your output voltage should be roughly or exactly 2.5 volts. And then when you compress the strain gauge, then you will change the output voltage in a certain direction. I just don't remember, but we will measure it. And then if you do a tension on your strain gauge, so for example you bend it in the other direction than in compression, you go towards the other voltage. I will show it what it is. So you can still stay within the rail or supply voltages, 0 and 5 volts, but you can detect both compression and tension applied on the strain gauge, and that's very smart, I think. And basically the trick behind is that the values of the components. So the nominal values of these 3 resistors should be smaller than the nominal value of the unstrained strain gauge. So these are 348 ohms, and this guy here, the strain gauge, this wire goes here, that is 350. And actually I built several of these circuits. I have one more, for example here, and you can see that these resistors are smaller. Actually those are like high precision 350 ohms, and this circuit doesn't work. And the simple reason is because the unstrained strain gauge, the real value will be somewhat below 350, and this will be also somewhat below 350, or these three like physical resistors, but they will be still larger than this resistor, and that will unbalance the bridge in a way that here you will get positive voltage, and then that will mess up the rest of the circuit. So here it's just a very smart and nice trick that these values are actually smaller. So when the bridge is unbalanced, the negative voltage is always staying below 0 volts. So it's always a negative voltage. And then here we invert it in the first stage, if I'm not wrong. And then in the second stage, we just keep it as it is. We just shift and amplify the voltage again. And then here we measure it on the output. So this is basically the basic working principle of this circuit, or for that matter, this circuit. But then, yeah, if you want to study this circuit and measure the stuff on it and understand it, it's hard. I had to do it, but it took some time to reverse engineer everything and then find the connections. So therefore, we have this circuit, which, if I haven't mentioned it enough time, can order from my PCBWay project page. So this circuit can kind of replace this if you also want to study the working principles of this thing. So yeah, enough talk. Let me power this up, and then we will measure each of these values here. So then I can check against the calculations. So let me do that, and then we will see what are the values. So I zoom out because we want to see the voltage values as well. So I will note down all of these from the video, and then we will be able to compare it against the calculations. So here I connected a 5-volt power supply, so I turn it on. You see the LED is on now. So let us check the first thing, which is the 5-volt supply, just to make sure. So we have 5 volts there, and then we can check the reference voltage. That is, yeah, 2.5-ish. And then here I can check the Wheatstone bridge, and I chose the left side as the negative, so I put the negative there and the positive is here. And now you see that we have a negative output voltage, 2.7 millivolts. So that's what we have with the unstrained strain gauge. And then if I check the positive or the non-inverting input, we have 1.2188. And then in the negative, we have 1.2207. So that's that. So once again, we measure 2.7 millivolts here. So this will be further amplified with the first stage. So the first stage output, FSO, is here. So now you can see that instead of, let's say, 3 millivolts, we have almost 190 millivolts. So here we have 60-something times amplification or gain. So then this 0.2 volts rounded will go to the next stage. So first, the second stage positive is this 0.2457 volts, and then the negative side is 247. So the difference between them is 0.01 volt, and then if I check the ground and the second stage output, we got 2.5 volts. So obviously I already changed the value of this potentiometer, so we get 2.5. So I can demonstrate how this circuit works. So now you see that when we started, this was the output voltage of the strain gauge or the Wheatstone bridge directly, and then we applied a quite large multiplier and we got 2.5 instead of 2.5-ish millivolts, we get 2.5 volts, so roughly 1,000 times amplification or gain. So let me do something. So I have these tiny clips for my multimeter. So let me use them as probes. So we measure the output voltage, and now I pick this thing up. So now I will apply tension on this. So if I bulge it this way, there is a tension. And this is what I did not remember about, is that if I put tension on the strain gauge, the output voltage is dropped towards 0. You can see the more tension I applied, the lower the voltage is. And then if I apply too much, then I just simply hit the rail, which is the negative rail or the 0 volts. So this is what I can measure. And then if I bulge it upwards, so towards myself, then you see that the output voltage is increasing. And this is when I apply compression on this thing. And now I hit the other rail, which is the positive rail. So this was the supply voltage basically. And then when I release, we go back to the, let's say, 0 level or baseline. So this is the voltage which we can read when the strain gauge is unstrained. But you can see that it's really sensitive. If I just put my finger on this and just press on it, then you can see that we can pick up changes. Or we can even try a bit different thing. I just rearrange the stuff here. So now I just clamped this cantilever in, and we can see how sensitive this is. And it's very sensitive, as you can see. So I put just barely any weight on this, and then now we are at 2.377, and if I remove this, 2.47677. So it dropped. Or maybe I can try even less weight. I will just find something. Yeah, probably this is out of tolerance. This is just a piece of a needle and with a string. But maybe if I use this. Yeah, this seems to make a difference. So now 4753 something, 49. So this one is detected, as you can see. So now you can see that the circuit works, and hopefully you could understand how it works. But still, I need to measure one more thing, because now I have to show you what is the value of the unstrained strain gauge, of course. And I also want to show you what is the value of the resistor here. Basically, the potentiometer is just two resistors, because this can be imagined as a voltage divider. So there are two resistors in that voltage divider, and depending on the position of the screw, the top and the bottom resistors in this voltage divider are sharing a different proportion of the nominal resistance of the potentiometer. And then we will measure that. So here we go. The screw side was looking downwards, so that means that the bottom one is the pin number 1. So I think the simplest thing is to put the black probe here in the center, and then we measure this first. This is almost center. Now you can see the resistance as well. So 451.8 ohm is the pin number 1, and then for the other it's 659.7 ohms. So I want to show these because we will use these values in the calculations. And then we can also do the same exercise with this guy here. So hopefully you can see it. So the unstrained strain gauge has 348.2 ohms as resistance. And just for fun, you can see that it changes if I bend it. So now I'm compressing it and the resistance drops, but it's like 1 ohm if I bend it too much or a lot. And if I make it into tension, then you can see that it changes. So the strain gauge works. So now I know all the values of the components in this circuit, including this guy here, the strain gauge unstrained value. So all we need to do is we need to confirm these values with some calculations or simulations. So let's head over to my computer and see if the circuit really gives similar values as the values from the calculations. So this is the simulation. I assembled this circuit in Volstead, and this is a free tool. I really recommend it because it can help you to understand how the circuits work. Of course, this simulation is just a set of equations, and I checked some of these values. I put the calculations on my website. I used the nominal values of the other circuit, the one that I reverse engineered, and I calculated those noticeable values with formulas, and then I checked it against this simulation, and they seem to match. So what I try to explain here is that whether you use the textbook formulas or you use this simulation, you get basically the same results. But we do not get the same results here as I got with the measurements of the multimeter. And there are several reasons for that, so I will try to explain them. Hopefully I will be able to explain them properly, but if you discover any mistakes or errors or something with my explanation, please let me know, because I also want to learn from these things. So what we have on the left side here is our Wheatstone bridge, and if you remember, we picked 348 nominal resistance resistors. Those are these three guys. So up here, the two guys, and this one here. So I measured them with a multimeter, and these were the resistance values. So the first thing is that the multimeter is not necessarily showing the exact precise value. So that can introduce some error in the results. And also these things have tolerances as well. And when I put them in the circuit and I run them, they can drift and so on. So they might not have the exact value that I measured at the moment before soldering them into the PCB. And then the bottom left corner value, you can see that that is noticeably higher than the other three. This is the value of the strain gauge. And the same applies for the strain gauge. It can drift a little bit, and it can have a little bit different value when it is finally inside the working circuit. So then we feed the circuit with this 2.5 volts, 2.485 to be precise, and then we measure the output of the Wheatstone bridge. And I explained it earlier that we need to have negative voltage here all the time, otherwise the rest of the circuit will not work. And we have negative voltage, but we have minus 1.921 millivolts instead of the minus 2.73-ish millivolts, which we would have here. So then that's not good. And also I measured the two output sections of the Wheatstone bridge. So this is the negative side on the left side, and that should be 1.2446, but this is 1.2436 volts. So that's a bit on the lower side. And then this is supposed to be 1.2418 volts, and this is 1.2417 volts. So it's a little bit lower. But the the main thing is, or one of the main things, is that the output voltage differs, and that basically destroys the rest of the circuit, because then what happens here is that on the first stage output, at this point, we just get 95 millivolts. But when I measured my circuit, I got 191 millivolts. So we are off by 100 millivolts basically, which is a lot. And then, as you can see, the output here is actually clipped, which means that we supply the maximum possible voltage out here, and that is the 5.027 volts. That was my 5-volt supply voltage, and we supply that on the output instead of the 2.5 volts. And that is based on, or that stems from the thing that we don't have the proper output voltage here. And then also one thing that I have done here, that is basically this part up here. So I mentioned that we need to measure the two sides of the potentiometer, and I split up the potentiometer into two resistors accordingly. So this is the side number 1 and this is the side number 2, let's call it like that. So when I measured the resistance between the pin number 1 and 2, that was 451.8 ohms. And when I measured the resistance between pin number 2 and 3, that was 659.7 ohms. So then basically these two resistors mimic the potentiometer. And then obviously here where we have the, let's say, the output of the voltage divider, that is the wiper of the potentiometer. And then that goes to the non-inverting input of this second stage. So that this will provide us the shifting from the zero. But you can see that we don't get the same values that we measure. So one thing that I can trick with is I can change the resistance of this strain gauge, or the simulation of the strain gauge, to get the proper output voltage here. So let's change this resistance to another value, so I get the same-ish output voltage. So now what we have here is minus 2.705 millivolts. And this might not be the best solution, because I just changed the left side of the Wheatstone bridge, so this voltage divider only. And actually we should modify both sides so I get the same output voltages as I measured, but now we just go with this. So now what I have here is I have a slightly higher voltage on the, let's say, negative side of the Wheatstone bridge, and now I have minus 2.705 millivolts, which is nearly the same as minus 2.73 millivolts. So maybe I can further increase this, let's say 88, just to get that voltage. So something like this. So now on the negative side I have 1.2445 instead of 1.2446, so it's close enough. And here obviously we did not change this side of the voltage divider, so we remained at the same. So 1.2418, and we should have 1.2418, so it's okay, let's say. So then what we have here is the first stage output, and now that increased to 135 millivolts, but it is still not 191 millivolts. Therefore, we are still in trouble with the second stage, because it is still clipped. So we still produce the maximum possible output voltage on the output of this bridge. So here in the highlighted part, we have a differential amplifier, and if you know this kind of circuit configuration, you know that basically what we want to have here is we want to have very tight tolerances with these 4 resistors, which basically control the gain and everything for this differential amplifier. And the problem here is that first of all, my values are slightly different. So one of the resistors, this one here, the 6.9 kilo ohm, is 6,942 ohms, and this guy here is 6,954 ohms. So they differ a little bit, and their tolerance is also only, in quotation marks, 1%. However, we could buy 0.01% tolerant components, and in fact they should have been used in this configuration. Or one could say that actually we should ditch this wall circuit after the Wheatstone bridge, and we should use an instrumentation amplifier. And actually that would be the solution, but here first we are focusing on this circuit, so we want to understand it and see how it works. So what we have here is one problem which could come from the real life circuit, is that these parts are not tightly matched. So then actually that could cause that I'm reading 191 millivolts instead of this 135. And I checked it with the other equation that I mentioned previously, and that also gives very close value to this. So definitely this simulation seems to be more acceptable than my measurements. So then moving to the second part, where we use the potentiometer to shift the output voltage, we can actually play around with the second part of the potentiometer, so the one which is, let's say, closer to the ground, or the portion which is between the wiper and the ground, that can be adjusted. So I change it a little bit, let's say to 400, and now you can see that we started to drop the output voltage. And in fact, if we go even more down, then we can see that we can actually shift down the voltage towards more acceptable values. And then if I change the strain gauge to something, I just change it slightly, then you can see that we have a corresponding response on the output. So this seems to obey the behavior of the circuit, so it works as it should. But obviously there is something wrong either in the built circuit or with the formulas, but I would believe that it's just the circuit and the tolerance of the components which is messing things up. So I change this back. And I change this as well. If I remember correctly, it was something like this. But then there is one interesting thing which I have discovered here, and it doesn't make sense to me, so maybe there are people out there more experienced with these calculations and with this specific simulation tool could explain this to me. So we know that we have these op-amps, and their gain is controlled by the proportion of these resistors, or the proportion of the resistors which are, let's say, placed around it in certain configuration. Obviously here it's a differential amplifier, and we can say that these are identical here and these are identical here as well. So then if we take, let's say, just the negative feedback part of the circuit, so this guy here, then the gain actually is this guy divided by this guy. So 338.8 thousand divided by 7,000. That will give us the gain of this first stage. But if I double click this, I can modify the gain here manually. And there is a magic number which is around 2000. If I apply this, our measured voltage will pop up here all of a sudden. and I just don't know why. And also now I could see that the voltage drops here, and that I again don't understand why. Probably it's because somehow, of course, this whole circuit here loads the Wheatstone bridge. And of course, if you load the bridge, then it will be different current drawn from it or through it. So therefore, the output voltage might be changed. But I need to take a closer look at this. But one interesting thing first here is that I can find a magic number for the gain, which is now here, happens to be 2000, to get the desired output voltage at the first stage, which I have measured with the multimeter. And obviously I can do the same here. So here we have, let's say, infinity gain, but let's change it to 1. And magic again. Here the output voltage is 2.529 volts. And when I measured the output voltage with the multimeter, it was 2.503. So it's very close to this. It's basically just 26 millivolt off, which is, let's say, close enough for me. But yeah, so I don't know what causes this or what's the exact explanation, but I wanted to mention this because it's an interesting phenomenon that we can have some, let's say, fake values for the gain, and we can, let's say, adjust or trim this value despite the fact that they don't correspond to any physical value, that I get the same values as I measured. And yeah, that's all. So you could see that my circuit works, or the circuit that I built based on the other circuit works, but for some reason the calculations are not the best. So maybe for the future I will look for some more precise resistors, and I will try to rebuild the circuit with those parts, and we will see what happens. But also, since this is the first step towards operational amplifiers and their use, I will of course build a instrumentation amplifier as well to make better use of our op-amps. So this is where I will stop with this video. So I hope it was useful to you. Don't forget to visit my project site on PCBWay's website, and if you want to replicate my project, probably with more precise resistors, then you can reach all the resources there. Also go to my website, because I wrote a big article about this thing, and I added everything, all the resources to my website, so pictures, KiCad schematics, and all bells and whistles that you can imagine. So please visit my website. And if you want, you can support me via Patreon, so that allows me to basically buy more gadgets and make more content about that. So I hope you learned something. I hope you like this video, and see you in the next video.